Okay, so there's only two topics on this next test. One of them is implicit differentiation, and the other one is related rates. And they kind of, related rates, you need to understand implicit and to do this. Related rates is talking about more application stuff. So it says, implicitly differentiate the following formulas with respect to time. State what each rate in the differential equation represents. So just like we can differentiate with respect to x, if we have a problem with like an application problem, we can differentiate with respect to time. And they tell you what these formulas represent. So this first one is the surface area of a sphere. So each one is its own variable. Each variable is, but I want to do it with respect to time. And respect to time means that just like when we do it with respect to x, we do dy over dx. So if I'm doing a derivative with respect to time, I want to take the derivative of that variable over dt, which is time. So if I took the derivative of a, I'm going to say that's dA over dt. And then 4 pi r squared. 4 pi is just a number, so we don't need the product rule here. We can just leave that as 4 pi. But the derivative of r squared would be 2r, but with respect to time would be times dr over dt. And we could simplify this. We could say that dA over dt equals 8 pi dr over dt. And what does each of those represent? Well, dA over dt represents the rate at which the surface area is changing. I don't know that I'm going to write all these out because I write too big. And then the only other rate in this is dr over dt, and r represents the radius. So this is the rate at which the radius is changing. This allows us to do a lot of application problems as we do this. Okay, so volume of a sphere, kind of the same idea. If I'm going to take the derivative of, oh, it's broken. Okay, let's see if I can get this to work. If I take the derivative of v, that would be dv over dt, right? Again, 4/3 pi is a number, so that would be 4/3 pi, stays there. And then the derivative of r cubed would be 3r squared. And if I clean that up, the 3 would cancel this out, and this would be just 4, oh, I forgot my dr over dt. 4 pi r squared dr over dt. What does that represent? Well, the dv over dt, sorry, I'm struggling with my markers here, represents the rate at which the volume is changing. And the dr over dt means the same thing that it equaled up there. Okay? So, what about this one? It says a equals the square root of c squared minus b squared, where c is the constant. So notice that c is the constant, so c would be like pi, but a and b would be our variables. Where does this come from? This looks like a version of a squared, b squared, and c squared, only it's solved differently. If you think about this for a minute, we could rewrite this as c squared minus b squared to the 1/2 power. So if I took the derivative of this, this would be dA over dt equals, this is a chain rule, so this would be 1/2. Leave the inside alone, so c squared minus b squared to the negative 1/2. And then I have to go back and take the derivative of the inside, but c is a constant, so the derivative of a constant is just 0. So this would just be negative 2b dB over dt. And then I got to clean it up a little bit, right? So dA over dt. This could go to the bottom, so that would be the square root of c squared minus b squared on the bottom. This 2 would cancel out with this 2. So I would have a negative b dB over dt, or if you really wanted to, you could do dB over dt out here. Put it at the top. It kind of doesn't matter on that. What do those rates represent? They just represent the rate at which A is changing and the rate at which B is changing, right? So I'm going to say dA over dB and dB over dt. I should also do t. Equals the rate at which A and B are changing. If you just remember that a derivative is a rate, then that's what all these are. The rate at which whatever variable it is changing. What's my time at already? Okay. Volume of a cylinder. Volume equals pi r squared h, where r is a constant. So that's really nice. And that's because think about if you had a cylinder, even if you were talking about the volume of it, the volume would be the height changing up and down. The radius wouldn't be changing. So since r is a constant, we don't need to take the derivative of it. We don't need to do the product rule here. We can just say dv over dt equals the pi r squared is going to stay. Derivative of h is just 1, but then I would do times dh over dt. And what does that represent? dv over dt represents the rate that the volume is changing. That dh over dt represents the rate at which the height is changing with respect to time. Look at these last two. We could also do this with trig. We're going to look at some stuff with like a ladder falling down a house, and we would do a problem like this. But it says cosine of theta equals x over 15. So theta is a variable and x is a variable. So what's the derivative of cosine of theta? Well, it's negative sine of theta, but then the derivative of theta with respect to time would be d theta over dt. And x over 15, the derivative of that is just 1 over 15, but then that would be times dx over dt. And d theta over dt represents the rate at which the angle is changing. So the rate at which theta is changing. Dx over dt just represents the rate at which x is changing. So again, I'm not going to write those again because it's the same every time. All right, last one. This one's pretty exciting. The volume of a cone. So we have a cone here. This one, r is not a constant because the radius does change as the volume changes. And so r and h are both variables. So we have to do the product rule here. Take the derivative of a variable. You have to do the over dt. So this would be dv over dt equals 1/3 times pi r squared. So r squared is my first one. So I'm going to do 1/3 pi. R squared would be 2r dr over dt, leave the h alone, plus I'm going to leave all this alone, so 1/3 pi r squared, and the derivative of h is just 1, but I have to do dh over dt. And there's not a whole lot you can do to clean that up. I'm just going to kind of leave it as a big mess. But notice that this would be the rate the volume is changing. This would be the rate that the radius is changing, and this would be the rate that the height is changing. And so what this means is we can do a whole lot of stuff now. What I really like about this curriculum is they try to break it up for you in these next few examples. I'm going to try to do one of these examples with you, and then that way we can work on some in class, and we'll see where we get. But it says air is leaking out of an inflated balloon in the shape of a sphere at a rate of 230 pi cubic meters per minute. At the instant when the radius is 4 centimeters, what is the rate of change of the radius of the balloon? And so there's a lot of stuff in this. One, if they're talking about radius, if they're talking about the rate of something changing over time, then you're going to want to use a related rate problem. And so notice they kind of go through these steps. I don't always do it in this order, but these are good steps to help you. So it says identify all the variables involved in the problem. Well, we're talking about a balloon in the shape of a sphere, right? So we're talking about the volume of the balloon, and in a balloon, it only has a radius, right? So like V and R. And it says identify which, if any, of the variables in the problem contain stay constant. So if I have a sphere and air is getting put into it, is the volume changing? Yes. Is the radius changing? Yes. So there are no constant variables in this. Part 3 says identify the rates that are given and the rates you wish to find. So kind of look at the words that they give you. Air is leaking out in the shape at a rate of 230 pi cubic centimeters. So if you don't know what that is, looking at the units should help you. That is the units for volume. So they're giving us dV over dt is 230 pi cubic centimeters per minute. So if you really want to write that, cubic centimeters per minute. They tell us that the radius is 4 centimeters. I would kind of write that somewhere up at the top. What is the rate of change of the radius? So they're asking us to find dr over dt of the balloon. So it says, write an equation, often a geometric formula or trigonometric equation that relates all the variables in the problem for which a rate is given or for which a rate is to be determined. Substitute any value that represents a variable that is constant throughout the problem. It's important to keep in mind that you can only have one more variable than you have rates. You may have to make a substitution that relates one to the other. But in this one, we don't. Volume of a sphere, it's really nice on this first page here. They give us this. Volume of a sphere is 4/3 pi r cubed. So that's what we're talking about in this problem. So we're talking about volume equals 4/3 pi r cubed. Our volume and our rate, our radius, and that's what we have the derivative of. So then we're going to take the derivative of those. And so that's going to be, we just did it on the previous page, but dV over dt equals 4/3 and pi, it's going to stay the same, but then 3r squared dr over dt. And I could even clean that up and say dV over dt equals 4 pi r squared dr over dt. And now, step 6 is you should be able to plug in everything they give you to solve that problem. So dV over dt, they told us, is 230 pi, and I'm going to use my units on this just to show you, cubic centimeters per minute. I know they said up here that my radius is 4 centimeters at the moment that they're asking me about. So 4 centimeters, and then square that. And then I'm looking for dr over dt. And so now I'm going to just solve that. This would be 16, nope. 4 squared is 16 times 4 would be 64 pi. When I square centimeters, that would be centimeters squared. So I'm going to divide that over. So I'm going to get 230 pi centimeters squared per minute, cubed I mean. And I'm going to divide that by 64 pi square centimeters. And that should equal my rate of my radius. So the pi's cancel out. And 230 over 64, you can do that on your calculator, or you can give me an exact answer, I guess. But I got -3. Why is it negative? Oh my gosh, okay, I have to go back. Oh, it's leaking out. Okay, so this is really important. I just wrote 230 pi, but since it's leaking out, that rate would be negative, right? Oh, I about got the wrong answer here. Leaking out would be -230. So that's where you get -3.954. And if we're talking about the units here, these would cancel out with 2 of these, and it should make sense that my radius is just in centimeters per minute. And if the air is leaking out, the rate of the radius changing should also be negative because the radius is getting smaller. So I thought it was inflating a balloon. That's why I didn't put the negative with it. So that's the idea of this. This is kind of a long video, so I'm going to stop. But just know that there's a lot of examples of this, and that's what we're going to work on in class tomorrow.